All right, so with just Ohm's law, which is the V equal to IR, I is V over R, and R is V over I, moving around with these quantities, you should be able to discover in any DC circuit how much current is flowing in this segment, how much is the potential difference in this segment, and so on. And to do that, you should have some kind of creative logic, interpretation kind of skill. You have to have all those things, because you should know where you're going to start from, like which is the first part that you'll simplify, and then after that, what do you do? That future planning is also, it's a kind of planning thing. So yes, I'll do this, and probably I'll be able to simplify this, and then I'll simplify this. So in other words, you're trying to find out how many series combinations are there and parallel combinations are there, and then after that you just work it out and shrink the entire circuit to a single resistance, and then you can apply V equal to IR and find out the current. And once you find that current, then you can start branching that current and start exploring forward. Get it? That's what you've done. Now today we will learn a little more about DC circuits. The first thing is about EMF and internal resistance. EMF and internal resistance. EMF. EMF stands for electromotive force. So this is electromotive force. And what is that? That is the amount of work done to transfer 1 coulomb throughout the entire circuit, including the cell. Okay, so let's see now. If you have a cell or a battery like that, you have a resistance outside, and this we symbolize with the letter capital R, called external resistance. This is the external resistance. And then we have another resistance here, inside here. That's called internal resistance. That's called internal resistance. So if you connect this in a circuit, what exactly is happening from the time you connect in the circuit? Charges are going to be taken down. So charges are going to go this way, through here. That means some work has to be done, right? And then work also needs to be done to fight its own internal resistance, and then you come back here. The total work that the cell is able to do through a complete circuit, including itself, is called the EMF. Now in the previous class I must have written it as V, just like that, because I didn't teach you what EMF is. But now you understand EMF. So what is written over here on this battery, on this cell? What is written? 1.5 volts. What is that? That is the EMF of the cell. So what is being written on the cell? What is written on the cell is actually the EMF. What is the EMF of a car battery? 12 volts. Do you get it? So the EMF is what you're supposed to be actually calling it, not voltage. You can't say, what's the voltage of a battery? Nah, that's not a right word. EMF is the right word for it. It's of course measured in volts. This is also measured in volts, but just called differently because it kind of relates to how much work is done to drive coulombs all around the circuit. So electromotive force, like how much force to move electrons around, that kind of idea. So what is the electromotive force of a cell? How do I measure it? Okay, how do I measure it? How do you measure the potential difference across something? How do you measure the potential difference across something? You put a, so of course there's a current here, and the current here is I. So as the current flows through this resistance, there is a potential difference. Which end of this resistor is at a higher potential? The left side. And the right side is, so if I connect a voltmeter here, it's supposed to read the potential difference across that external resistance only. So a voltmeter's job is to only measure the potential difference. A voltmeter's job is only to measure the potential difference. It cannot measure the EMF. A voltmeter cannot measure the EMF. It can only measure the potential difference. I'm just going to give you another example over here. Let's say I want to know how much is your EMF. I want to know how much is your EMF. So I'm the voltmeter, and I want to measure your EMF. And what is your EMF? Your EMF means how much work do you do throughout a day? In other words, in 24 hours. How much work do you do from the time you leave from home? From the time, this is your home. That's where you leave from home. And that's where you go through all the hardships. And you go back. So if I want to measure you, think of it practically. I want to measure his EMF. What should I do? I have to measure your energies. So I have a book and I have a calculator and all that. I'm standing outside his door, waiting for him to show up. I'm standing outside his door. As soon as I see him come, I'll start, monitoring exactly what is happening to him. I see him come, and I saw him climbing stairs, MGH. Because he's doing work, right? MGH. And I keep calculating all the amount of work that he's doing from the time he comes up from his house. I check all the work he's done. He's coming to school. He's studying physics. I just calculate everything. I keep counting everything. And he goes back home. And as soon as he reaches here, that's all I can go. I cannot monitor him any further because I don't have access to his house. So I have a number though. I totaled up a lot of energy, and that comes out to something. Is that his EMF? Yes or no? No, that's not his EMF. That's not his EMF, because after he goes inside the house, is he doing work there? Yeah. But I cannot access his house, so I cannot measure it. As a voltmeter, I cannot measure him. Yes, Michael? Yes? Got it? Are you getting it? Okay, take your hands off. Good. So as soon as he enters here, I'm done. I have a number, but that number does not really tell me anything. Okay, I have 2000 joules, but is that his EMF? No, because at home, I don't know what he's doing at home, how much energy he's spending, is he studying, is he doing some weightlifting or something like that at home? I don't know, but all that counts, right? Even when you sleep, even when you snore, you're spending calories, you're doing work. So I need an account of how much you're doing at home, which I cannot get access to. So what am I? I'm just a voltmeter. What am I doing? I'm only measuring the potential difference outside your house. This is exactly how, because instead of connecting here, I can actually connect it here, right? No difference? Instead of connecting here, can I connect it here? Because this path, he's not doing any work. He's just getting transported from home to school. So not much is happening there. So I can just ignore that. So connecting here or connecting here won't make a difference. So basically, if I connect a voltmeter here, what will it read? Hmm?
It
It will still read the same thing that it was reading here. Although I connected across the battery, it will still read this. You understand what I'm saying? Because connecting across here and connecting across here makes no difference. It's the same thing. So I am actually checking how much energy he has, and all I have is external potential difference. But he's doing some work inside. If I get an account of that, then I can tell this is his EMF. How can I find this? How do I find V? How do I find the external potential difference? How much? How do I find it? This is IR. Now, on this account, how much is the potential difference inside here? Here. How much is inside? How much is the potential difference inside cell? I lower R. And if I add those two, I should get EMF. So write down this. EMF is equal to external drop plus internal drop. EMF is the external drop plus internal drop, which simply means EMF is equal to IR plus IR. That means EMF is equal to I times R plus R. So what is I? I is equal to EMF over R plus R. What is that meaning? This means current is equal to EMF divided by total resistance. Total resistance throughout the circuit. That's what it means. And this is the EMF. You can also call it total EMF. You know why? Because probably there's not one cell, maybe 3 cells. So if you have 3 cells in here, account for that. So the cells, you need to account for all the cells in here. So total EMF over total resistance, that will give you the current. The total EMF over the total resistance gives you the current. So what you have seen earlier, how did you do earlier? It's like V over R, but it's almost like V over R, but it's EMF over total resistance. So how do I find this current? I need to know the EMF, I need to know the external resistance and the internal resistance. You get it? I need to know everything. Any questions here? Let me know. Good? Okay. I hate this.
Yeah, that's Jerry. He's looking at the picture.
So you know the idea now. I'm going to give you some examples and see we'll see how it works. Just simple example. The EMF is 6 volts. Internal resistance 2 ohms. External resistance 4 ohms. Internal resistance 2 ohms, external resistance 4 ohms. Tell me the current quickly. 1 ampere. Right? Why is it 1 ampere? Current is EMF over total resistance, which is external plus internal. So remember, now in the previous problems we never bothered about internal resistance. Now we are bringing that in, that's all. So 4 plus 2 is 6, so 6 over 6 is 1 ampere. Now if this 1 ampere current flows across here, how many volts will be registered by this voltmeter? 1 times 4, which is 4 volts. You said 1 4? 4, 1 times 4. 1 times 4, which is 4 volts. Now, what happens to the current? The current is still going on. When the current flows through this resistance here of 2 ohms, how many volts will it drop? So inside here, there is a voltage drop of 2 volts inside. Inside it is. And if I want to measure that, if I put a voltmeter here, how much will it read? 4. It cannot measure the internal resistance, internal drop. That's why I said I cannot have access to his house. That's why I'm not able to read that. You understand? So a voltmeter cannot measure the potential difference that is happening inside the cell. Now let me ask you this. Which side of the 2 volts is positive? Which side is positive of the 2 volts? You know it is causing a drop of 2 volts here. Which side is positive? This side or this side? Which way the current is entering? The current is entering from here. So obviously this side should be higher than that. Make sense? Wherever the current enters, that's where you have high potential. When the current leaves, that is lower potential. Before the race, higher potential. After the race, lower potential. See here, the current is coming in this direction. So this is positive and that's negative. But the current is coming from here, so it's positive and negative. Yeah.
How do you get 4 volts?
Because it's the same wire that's connected here and the same wire that's connected here. Now I'm coming to your answer. Can you see this is plus, this is minus and plus here, 2 volts? EMF is how many volts? Which side of the EMF is positive? The batteries. How do you find the batteries positive and negative?
Big red.
This big line is what? And this is? That's how we check it. You know, the long line is positive. Yeah, the red and black. That's positive and that's negative. So 6 volts plus this side minus this side. But 2 volts inside, which is negative on this side and positive. So what is plus 6 minus 2? And that's what is recorded. So what the voltmeter records is an overall potential difference. The voltmeter is actually, see, this is how it is. The voltmeter is looking at the cell and saying, oh, I have plus 6 here. Oh, wait a minute, there's a minus 2 inside. So take it off. Get it?
So if you had like a 6-volt battery, and if companies wrote on the batteries the potential difference instead of EMF, they would be writing like 4 volts.
They never write the potential.
I realize they don't, but if. Like,
No, that depends on what you're connecting to.
Oh.
That's my next example. I'll show you if I connect something else, you see how it changes. Or let's say the internal resistance is now different. Now this is a different problem now. This is a different problem. You write it once again. This is the same thing. I'm connecting the same resistance. Internal resistance is 1 ohm. The internal resistance is now 1 ohm. So any resistance that is marked around the cell, any resistance that is marked around the cell is the internal resistance. Okay? Any voltage that is marked next to the cell, that is EMF. You understand this? Any resistance mentioned next to the cell, that is internal resistance. Any resistance that is mentioned, any voltage that is mentioned next to the cell, that is called EMF. Okay? So now, do the same calculations. What is the current here? Which is 1.2 amperes. So how much will this voltmeter read? How much will this voltmeter read? Is it 1.2 divided by 4 or 1.2 times 4? Read 4.8. 4.8 volts. That means you're getting more outside. Can you see that? You're getting more voltage outside. How much is the internal drop? The inside drop is 1.2 volts. Which side is positive? And now do the same thing. 6 minus 1.2 is what? And that's what it will read there. So that is going to read 4.8. This is 4.8 because it's the same connection. Now, is the same battery providing more voltage outside and less drop inside? See, this is a totally useless drop. This is a useful one. This is something that's useful, but this is useless. In the sense, it is of no good purpose. It's not going to serve any purpose. This is not going to serve any purpose. But this is what actually serves the purpose. Purpose like what? Light bulb. You connect a light bulb to a cell, a flashlight. Here's your battery, and here's your light bulb. So the voltage that's coming here is what makes the light bulb work. Is the light bulb working on 6 volts? No. The light bulb is only working on 4.8 volts. Where is the rest of the voltage gone? It's inside the cell. Is it going to be useful? No. So what is ideal then? What's ideal? If you know that this is useless, you like to have an internal resistance of 0. But the problem is, if you want internal resistance of 0, you need to have a huge power supply. So that's why I said a car battery has a resistance of like 0.1 ohms. Car battery has a resistance of 0.1 ohms. But when you're talking about a current of 30-40 amperes, even the 0.1 ohms will make a big difference. You know what I'm saying? Even the 0.1 ohms will make a big difference. If you're talking about a current of 30-40 amperes, 0.1 ohm inside the cell will create a big drop. So understand the idea of internal drop and external drop. Okay? Now going back to the same equation, EMF is equal to the external drop plus the internal drop. EMF is equal to the external drop plus the internal drop. So the lesser you have this internal drop, the more you're going to use this. This is a useful component, that's a useless component. You cannot use it. Now what have you learned about power? What's power? Go back. Power is equal to voltage. What's the electrical power equation? Go back and fetch it. IV. I times V is power. You all have it? Did I give you the other equations for power? Probably not. Now, this power equation is in terms of V and I. Now, if I use Ohm's law, I can replace one of these terms. So, since V equal to IR, and if I plug this right here, if I replace this V with IR, what is power equal to? I square R. This is the power equation in terms of I and R. Make sense? Now what is I equal to? V over R. If I replace this here, what do you have in this original equation? Power is equal to V times V over R. If I replace this here, I get V times V over R, which is So we have three equations for power. 1, 2, and the third one. So power can be seen as I square R, can be seen as V square over R, can be seen as VI. So you can measure the power that the television is going to draw if I know two things. One, either voltage, the next one's current. If I know the voltage and the current, I know how much power. But if I know the voltage and the resistance only, yes, I can find power. But if I know the current and the resistance, I can find the power. So you have three equations to play with to find power. You get it? Good. Look at this equation. Look at this equation. I'm multiplying the whole equation with I. If I multiply the whole equation with I, see what happens here. EI is equal to what? I square R plus what? Now what is this? What is that? It's power. Power what? Power external. This is the external power dissipated. External power dissipated. That is I square R. That is something that we are using. Like if you're connecting it to a light bulb, then it is dissipating the power in the form of light and heat. Right? If this is a heater, then it's only mostly heat. If it's a fan, if you're connecting a fan, then it is mostly in the form of mechanical energy and all those things. You get it? If I'm connecting this to a coil, then it is mostly a magnetic form of energy. So this is the external power dissipated. And what is that? Internal power dissipated. Internal power dissipated, which means what? The energy that is dissipated inside the cell. As what? Heat. As heat. It only comes as heat, nothing else.
So that's only for internal.
Yeah, this is the internal part of it. Yeah, heat is the only internal one. Externally, you can have it as light, you can have it as different forms of energy, right? But internal is like if this is a, if this one is a bell, then what will happen? The external power dissipation is more of sound energy, right? It's sending sound. So this can be of different forms, but this is only as heat. Now you know the reason why a cell becomes warmer when it starts getting used. If you use a cell, the cell gets warm. Have you felt the cell after using it for some time? Right? So, no? Like imagine you used cells in your remote control car or whatever, used it. And after that, after the use, immediately after the use, just open the thing and touch the cells, it'll be warm. Where is the heat coming from? That. But we don't want that because that heat does nothing. It's pure waste. Now let's take this example. Oh, by the way, what is this? What is E times I? What is E times I? What does it stand for? Power. It's also power. It's like VI. Can you see that? But instead of V, it is E. You know the difference between V and E now. V is only the power dissipated across 2 points. But E is for the entire. So this is the total power generated by cell. This is the total power generated by the cell. Okay? That's the total power generated by the cell. So the total power generated by the cell is going as external power and internal power. Now let's look at numbers. How much is the total power generated according to this circuit?
6.
How much?
6 volts.
No, how much is the power generated? EI. What is the generated power? E times I. 7.2 watt. Watt. That's why I said watt. 7.2 watt. 7.2 watt. Not watt. Watt. What is external power dissipated? Calculate that one. I square R. How much is I square R? I square R. 1.2 square times 4. 1.2 square. How much?
5.76.
5.76 watts plus. What's the internal power lost? 1.2 square times 1. 1.44 watts. Add this up, it should be here. Same, right? So this is the external dissipated power, which is good because that's something that we're using. What is this? That's the internal loss. It's a loss. This is something that is loss. So basically, when the cell is doing this much, that is a loss. We can't help it because it depends on the cell. If the cell has more internal resistance, then you're going to lose more and more. That's why when the cell becomes weak, the loss also equally becomes weak. Greater. Yeah. Go ahead.
Does that mean that like you can measure heat in terms of watts, like how much is dissipated, like how hot it gets? If the internal power dissipated can only be like.
If you can measure that, yes. If you can actually measure how much heat energy is coming out from there and measure the time, then you can actually figure out the power loss inside itself. It's kind of tougher thing to do, to measure the internal power loss. But if you know the current, you can figure that out. So what is ideally required is we try to minimize this internal resistance so that you can get more out the outside. You get it? So the idea of internal resistance is clear. So now, if I give you a problem where you have an internal resistance also mentioned, then you should take that into account. Like in last year, the previous problems that you've done, you did all this network, right? In the network, if there was an internal resistance, you should account for that also. Like you should include that into your calculations. You can't just ignore it. That's something that is going to make a change. Questions? The voltage which is outside the cell is called terminal potential difference. When you're actually connecting terminals across a cell, what you're measuring is called terminal potential difference, not EMF. Can you measure EMF? No. You can't measure EMF. Why? Because the moment you connect something outside the cell, let's say for example, let's say this is just a cell and it's 6 volt cell. If I just take a wire and connect right across, just across the cell, will it read 6 volts? There's no other resistance. Can you see? I've removed everything else, just the voltmeter. I just connected the voltmeter. Will it read the EMF? The answer is no. Why? Because the moment you connect something, that is the external resistance. This is your external resistance. So what's happening is the moment you connect the voltmeter, a tiny current starts flowing. A tiny current starts flowing. Because a little current is required for this voltmeter to work. Right? So a current starts flowing. And when a current starts flowing, will there be an internal drop? Yes. Which means what you're measuring is not the EMF. How can you measure you can't measure it. if you can actually stop this current completely, then whatever potential difference exists across the cell is the EMF. Okay? If you can stop the current completely, if you draw nothing from a cell, what is existing across the cell is the EMF. But the moment you start drawing something, then it won't be the EMF. Then it's called terminal potential difference. Terminal potential difference. Now when your car battery, let's say you're talking about a car battery. When your car battery is operating, let's say your engine is not on, your engine is off, but you turn the lights on. You turn the lights on. The engine is off, you turn the lights on. So what is happening is your car battery is being used, right? How many volts is supposed to be the EMF of a car battery? 12. That's the EMF though. When your lights are on, it will drop. If you connect a voltmeter across the cell, across the battery, all right, here's the car battery. If you connect a very ideal voltmeter across it, it will read 12. Ideal voltmeter, right? Or if it is nearly ideal, then it should read nearly 12. Very nearly 12, almost 12. That is when the battery is not being used. But as soon as you connect some light bulbs, and the light bulbs are turned on, what's happening now? The light bulbs are working because current is flowing, right? And when the current is flowing, there is an internal resistance which is going to take this drop. So there is an internal drop right there. And because there's an internal drop, will this read 12 anymore? It will read less. You can check this out in your car, actually. You can check it out in your car. Check the battery voltage. It will read slightly, almost 12. And then turn on your headlights. Just turn on your headlights and you'll see the voltage kind of dropping. It'll drop. As soon as you turn on the headlights, immediately the voltage will kind of drop to maybe 11.5, 11.6. It depends on the battery's condition. It'll drop. If it's a weaker battery, it will drop to even 11 or 10 point something. So the terminal potential difference across a battery can even fall that much. Right? You understand? Now, if you start the car, as soon as you start the car, what is the car doing? What is the alternator doing?
Recharge the battery.
The alternator is recharging the battery. That means there is a current going into the battery from the alternator. That is the recharging current. It is going into the thing and going out. So which way is the current flowing when the battery is being charged? So let me draw it again. This is the battery, 12 volts. The current is now going that way because you're forcing it. Normally how the current will flow? It will go out of the cell, right? So when the cell is being used, when the cell is being used, the current comes out. When the cell is being charged, the current goes in. Right? Now suppose the internal resistance, if the internal resistance is 1 ohm, and if this current is 2 amperes, the charging current is 2 amperes. How many volts is across here? How many volts across the internal resistance? How much? 2 volts. And if I put a voltmeter across here, how much will it read? Say it again.
0.
14. Why? Because when the current is flowing into the cell, the current is going this direction. So which end of the two is positive? And what about the cell itself? So what's the total? It's 12 plus minus 2 plus minus. What's the total? So when the cell is being charged, check the voltage across the battery. It'll read 14, somewhere in that region. So when your car engine is on and the alternator is on, check the voltage across the battery. It will be more than 12. But when the alternator is off and the cell is being used and the battery is being used like this, it will be lower. Let's say, for example, here, if I'm taking 2 amperes out and this is 1 ohm, which way is the current going? From this side. So this is plus minus 12 and this is going to be 2 volts. Which side is positive? The right side is positive. So how many volts will be seen here? 10. So understand this concept. When a battery is being used, the terminal voltage will be less than the EMF. When a battery is being charged, the terminal voltage, you understand the term terminal voltage? Terminal voltage is more than the EMF. Okay? What is the equivalent resistance? What is the equivalent resistance of this whole thing? Like if I put a resistance meter here and here, what will it read? What is the equivalent resistance of this entire thing? Quick. This should be the easiest problem actually, if you look at it, because the current comes here, splits up into 2, joins, these two are in series. And these two are in series, and those whole things are in. All that you have to do is 7 plus 5 is 12, 3 plus 1 is 4. So the 12 and the 4 are in parallel, finished. 12 times 4 over 12 plus 4, the answer is 3. Now making some modification and tell me what the answer is. Are 7 and 5 in series? Why do you say no? Because there's some branching here. Are these two in series? No, because there's a branching here. Are these two in parallel? No, because there's something in between here. Are these two in parallel? No, there's something here. So you cannot figure out a single series or parallel combination. There is not a single series or parallel combination. Then how do you simplify the circuit? You cannot simplify the circuit. If you want to find out the internal resistance of the whole thing, which is equivalent resistance, you cannot just find it out by using simple rules that you've learned so far. And that is why we're going to learn the new rule, which is called Kirchoff's laws. Kirchhoff's laws. We need Kirchhoff's laws. Ohm's law is just not enough. So we are going to learn Kirchhoff's laws. Okay? So when you have a network, why is it called a network? Because actually it looks like a net. Tangled. Can you see that? That's why the network. Network. It's like a fishing net. Like it goes this way, goes this way, goes this way, goes this way. It's going everywhere. Right? That's exactly why networking, computer networking is also called a network, because it's like connecting this. So when you connect everything, you call it network. So we wondered why the word network. Here's a network. So when I drew that one, you saw that you couldn't find out a single series or parallel combination. That's because it is connected like a net. And to solve such things, we need Kirchoff's laws. There are two laws of Kirchoff, and they are here. The first law of Kirchoff says the sum of currents at a junction is equal to 0. The sum of all the currents at a junction should be equal to 0. Symbolically, it is represented as sum of all the currents is equal to 0. This is a summation sign. This is a summation sign. Sum of all the currents at a junction is equal to 0. Now, what do you mean by a junction? I've used the term before. Huh? A connecting point. Right. So, if a wire is going like this, if a current is going this way, let's say current is going here, okay, and some other current is coming from here, that's I2. Like two roads coming from here and coming from there, two roads, and they're coming to this junction, and some of this traffic goes here, that's I3, and some goes here, that's I4, and some goes. So this is a junction point. Where, yeah.
Does little I have any meaning over the capital I?
It's the same thing. Little I or small or the capital I. So you can see that some are coming in, some are going out, right? Tell me the total traffic at the junction. 0, because there are some coming in, some going out. The algebraic sum of all the currents at the junction should be equal to 0. That means all the incoming ones, if you consider them as positive, and if all the outgoing ones take it as negative, sum it up, it should be 0, because no one is going to park right at the junction. So therefore, and you can't stop. If current means what? Current is flowing charges, no stopping, just continue like traffic. So how do you write this equation? You write I1, if you're going to consider the currents coming in as positive, I1 plus I2 minus I3 minus I4 minus I5 should be equal to 0. This is the first law of Kirchoff. You know what? You already have used the first law. You have already used the first law when you solved the previous problems. How? Remember the situations where the current coming from here was 1 ampere, and then it came to a junction and the current going this way was like 0.67 amperes, and immediately you concluded that this one was 0.33 amperes. Remember that?
Yeah.
So we already used Kirchhoff's first law, because that's how we concluded that this is 0.33 amperes. How do we know this is 0.33 amperes? Because we already used the Kirchhoff's first law. And why is Kirchhoff's first law true? Because of conservation of charge. The charge is coming in is 1 coulomb every second. The charge is going out should be the same.
That's weird.
Okay? The charge is coming in and the charge is going out should be actually the same. So that's why you see the total. So here, 1 minus 0.67 minus 0.33 equal to 0. That's exactly Kirchhoff's first law. Second law talks about closed loops. So in any closed loop, the algebraic sum of the EMFs plus the algebraic sum of the potential differences should be equal to 0. The algebraic sum of the EMFs plus the algebraic sum of the potential differences should be equal to 0. That is, in any closed loop. What's a closed loop? A closed loop is like starting from one point, it should be a complete loop. Okay? That is called a closed loop. Now, you're going to do some work on this to understand how it works. So I'm going to give you a circuit diagram. Let's do a problem. Now, if I ask you to find the current here, of course this is a simple problem. This is not a network, big network. This is something you can use Ohm's law. Can anyone tell me what's the current right there? Quickly. You can ignore internal resistance, okay? Ignore the internal resistance. 1 ampere. It's 1 ampere. Why? Because these two are in parallel. Can you see that? And this is 6 in series. So 3 for this, 6 here. So total is 9. 9 over 9 is 1. So you already know the current is 1. Now, imagine this is a complicated circuit and you don't know how to do it. Then we use Kirchoff's laws. So I'm going to solve the same thing that we did just easily by using Kirchoff's laws. How do you do it? You have to look for how many closed loops do you see in this? How many closed loops do you see? 2 closed loops? Look again. Okay, if I start from here, and if I do it like this, if I go like that, if I do this, that's 1 closed loop. If I start from here, go like this, if I go like that, that's the next closed loop. If I start from here, if I go like this, that's the 3rd closed loop. Closed loop simply means like completed circuit. There are 3 closed loops here. So you need to work on at least 2 closed loops to solve this problem. But before that, you have to apply the first law of Kirchoff. What is it? So, do you know this current? No? So call it I1. Just call it I1. You don't know the current. So the first part of this problem solving is assuming the current directions and current values. So this is I1. And watch. I1 is coming here. I1 comes here. What happens at this junction? It splits, right? And so let's say I2 goes here. If I2 goes there, how much goes here? I1 minus I2. That is where we apply the first law of Kirchoff. So the current here is I1 minus I2. And this I1 minus I2 goes here. And I2 goes here. And then together it becomes I1. This is the first part of your problem solving. In the next class, I'll show you how to use the second law here and get to the answers.